Alrighty, let's see. Oops. There we go. Hey there. What up? Okay, let's see. Sorry, I'm just setting up all my stream windows. And I'm here to wish you good afternoon. Day 2, chapter 1. We're going to be diving in. Oh, let's put this. Okay, sweet. Let's see. All right. Hello to everybody. Just logging in. Sorry, I'm a couple, like 5 minutes behind our class start time. All right, I think I'll be diving in just a second. Chapter 1's a introductory chapter. Nothing too crazy. I wanted to point out a couple things by way of announcements. A couple I don't know, news items, I guess, would be how I put them first. I don't know if anybody had went back to rewatch the stream from yesterday, but if you have, you've already seen this. If you haven't, this might be a bit new, but all of our videos up in here, after I live stream them, I go back and I add timestamps to add timestamps in the comment section. So if you go back and look at yesterday's video, and you were like, where was he was talking about? Let's say you wanted to find, I don't know, when we were talking about my mind's drawing a total blank on everything we talked about yesterday. The syllabus quiz, for example. You wanted to go back and find the syllabus quiz. In the comments, you can see I kind of catalog things, and it'll say syllabus quiz, and then in parentheses there will be a time, and there will be a link there you can click on, and it will take you right to that spot in the video where that is. So I kind of add a table of contents. I know these videos are long. One of some of the feedback that I got last semester that was very helpful was that I had a few students tell me, it'd be better if these videos were shorter. Like an hour and a half is a long time to kind of sit and watch a YouTube video. And the reason why they're that long is because that's the time slot we have allocated to the course. So it's a time that people have signed up for, knowing okay, this time is going to be chemistry time. So to kind of compensate for the fact that they are large and a little unwieldy, I add those time steps to the comment section. That way it makes it easier for you to navigate if you're going back and review and you just want to see that one topic and you don't want to have to wade through all the other hours of video. Oh, Angela, I'm glad you find the timestamps helpful. Yeah, so I do it to be helpful, and I want to make sure that everybody knows that this is a resource that you all have available to you. Okay, so that's one item. Second item is the syllabus quiz. All right. With the syllabus quiz, I want to stress that it is due at 11:59 p.m. Today. All right. And the reason why I want to stress this is I have a wait list of humans as large as the class. Even people emailing me, now the wait list is officially closed, but saying, is there any way I could possibly add? A lot of people are hungry to get into this course. And so I'm doing this kind of as a way to make that opportunity available to them. If you do not turn in the syllabus quiz, if you haven't already, by 11:59 p.m., I will drop you and give your spot away to a waitlisted student. So it's been in the syllabus. It's on the cover page of our Canvas course. I announced it last lecture. I'm starting this lecture by saying it. There's going to be no grace here if you don't make it in on time. I checked this morning my email in Canvas, and about 60% of the class had filled it out. So anyways, if you're in the 40 who hasn't, your spot will go to a waitlisted student if you don't get this in on time. So just if you want to be in, you've got to do this. If not, you will be dropped. All right. So that's the second piece of business. The third piece is a little more fun. So I when I taught in person, I would always do like song of the day. Sorry. A couple things in the comments. Yes, Prarantha. Wait, hang on. Prarthana. There we go. Okay, I'm sorry. I will get your name right, I promise. This is only day 2 of trying to say it. I did get your email. Submitting it by email is totally fine. Jen, you noticed that the comments sidebar was not showing up. Yes, totally. You know what's so funny is when I noticed that too. That when I was timestamping the video, that it wasn't the comments, the live comments, were not available with the video. I'm not sure why. Every single video that I did last semester had the live chat visible while it was scrolling. So I'll go take a look back and check out why that wasn't the case. I will figure that out because I think that it's good. Oftentimes I'm responding to questions that are put into the live chat, and so seeing that is useful. I will totally check that out. Oops. Okay. All right. Oh, right. So today, our daily mixtape is titled "For the Deaf." You can find I make these on Spotify. You can listen to all of them for free, or if you pay for Spotify, you can do that too. But you can always listen to Spotify for free. I post those links in the comment section as well, so you can check out those beans if you're needing a little study motivation. It's usually what I'm listening to as I put together the class for the day. So today was a pinch of Queens of the Stone Age and some Soundgarden. No Iggy Pop, ironically enough. We'll work Iggy in one of these other days. All right. So all that being said, let's go ahead and start talking about some chemistry. So this is a chemistry course after all, and chemistry chemistry is, if you were to boil it down to one single nugget, you'd have to say that chemistry is the study of matter. Right, it's the study of the stuff that makes up the universe. Now the universe is made up of two things, right? There's matter and there's energy, are the two fundamental quantities that we have in the universe, and chemistry focuses on matter. And this is what the book would tell you, and though the book isn't wrong, I'd like to add a shade of meaning here, right? The chemistry is about the study of matter, but I want to add kind of what's the word I'm looking for? Yeah, just a shade of meaning. If you think about what we're known for as chemists, right? What our field. When I started spelling chemists. You would say, like, if I asked you to fill in the blank here, chemical blank, you would, if I were to ask you, what's the first word that comes to mind when I say chemical blank? And probably the word that would come into mind is reaction, right? Or reactions, chemical reactions. That's the thing that that our field is kind of known for, that my field is kind of known for, right? And what a reaction is, a chemical reaction is the transformation of a structure, of the structure and composition of matter, all right? It's chemical reactions are how matter change their structure and composition. And so really, I would kind of have to agree with Walter White from that first heartbreaking episode of Breaking Bad, where he says that chemistry is the study of change, right? And reactions. This is true because reactions are the processes by which matter changes its structure or composition. So it's not wrong to say that chemistry is the study of matter, but what we're going to be focusing on is how matter changes. Oh, did you hear that phone call? That is my mom. I'm texting my mom. There we go. And I'm silencing my phone. Okay. Sorry. I apologize. I thought that phone was already quiet. Okay. Reactions, chemical reactions, how matter changes. Now, when you ask, so we're talking about matter, right? And matter, the proper definition for matter is anything that possesses these two qualities. It has mass, which is another way of saying it weighs something, and it takes up space. All right? If something has mass and takes up space, it's classified as matter. And matter comes in three different flavors. All right? You have solids, liquids, and gases. All right? you've got the solid phase, the liquid phase, and the gas phase, excuse me. All right, and there are a lot of differences between these two phases, but you can, one way to kind of look at them and differentiate them is by looking at the shape of each and the volume of each. All right, if you look at the shape of a solid is defined. It's definite. Ooh. All right. The shape of a solid is defined. It's definite. It has a fixed shape that doesn't change. All right. And on the opposite extreme, on the opposite end, you have a gas, which is an indefinite shape. All right, if you have a solid object, you can pick it up, you can move it, you can place it here or there. If you have a gas, its shape is amorphous. There's no, it fills whatever space you put it in. And that could even be changing as that space changes, right? You can look at the shape of matter. You could also choose to look at the volume, right? The volume of a solid is definite, right? It'll always fill the same amount of space. It won't expand or, I mean, there's small changes to volume, right? We know that concrete cracks. Oh, Susan, great question. Susan just asked in the comments, is fire considered a gas? Fire is actually pure energy. Fire is actually pure energy. So we said matter is anything that has mass and takes up shape. Energy does not have, takes up shape, takes up space. Energy has no mass. It's the other kind of fundamental quantity in the universe that we can measure. We can measure matter, and we can measure energy. So fire is just pure energy. It has no mass at all. And we'll be talking more about energy as we get deeper into the semester for sure. All right, so volume, the volume of a solid is definite. As I'm sure you can guess, the volume of a gas is indefinite. So I forgot an I up here. The volume of a gas is indefinite, and that's because the amount of space, the volume that a gas takes up, can constantly change. You can compress a gas so it takes up less. You could have a gas expand so it takes up more. It's not definite. Now, liquid is that middle child, right? I feel like solid is like the firstborn, very type A, very like driven. Gas is like the youngest, indefinite, all loosey-goosey, all over the place. And liquid's that middle child that's balanced. Now, as you know, a liquid has no definite shape, right? Right now, this liquid in my Rick and Morty coffee mug is taking up the shape of the coffee mug, but if I should choose to spill this on my lap, it'll take up a different shape, right? A shape that I don't want to explore right now. So the shape that a liquid takes up is indefinite, just like a gas, all right? The shape of a liquid is indefinite, but its volume is definite, all right? The volume that this coffee takes up will be the same no matter if it's in the cup or in my lap or in the coffee maker. The volume won't change even though the shape does. All right, so solids, the most rigid phase of matter. Gas is the most flexible, and liquid is that middle child. It's got some constriction with its volume, but it's got less restriction when it comes to its shape. All right, we've all interacted with solids, liquids, and gases for most of our lives, but I kind of wanted to lay out, kind of give you a way of thinking about analyzing, categorizing liquids, solids, and gases, as well as introduce the three phases formally in our class time. All right, now, matter, we said that chemistry is the study of matter, but really what we're interested in are chemical reactions, right? How matter changes. And there are two different types of changes that matter can undergo. There is what we call physical change, all right, and there's chemical change. First, let's talk about physical. All right, physical change is when physical change is a change in matter that does not alter the chemical structure, or I should say does not alter its chemical structure. All right, so an example of physical change would be cutting my hair. All right, that would be a great example of physical change, because the molecular structure of my hair is the same before and after I cut it, right? It's the same when it's all attached. It's the same when I cut off a piece. It's hair before and after. Another great example of a physical change would be, I did not mean to do that in blue, would be freezing. Right? If you freeze a sample of water, it's H2O when it's liquid, it's H2O when it's ice, right? The chemical structure hasn't changed. And that makes it a physical change. The chemical structure is the same before and after. That means your change is a physical change. All right, physical change and physical changes are contrasted with chemical change. All right, a chemical change is a change in matter that, oh, snap. I said that physical change was a change that does not alter, right? But then I wrote does alter. That does not, my apologies, alter the chemical structure. That's physical change. Chemical change is a change in matter that alters the chemical structure. All right, it's a change that alters the chemical structure of matter. So an example of chemical change would be instead of cutting my hair, if I burned my hair. I should say burning. Burning my hair alters its chemical structure. After burning my hair, it's no longer hair. I don't have any hair molecules. All I'd have would be carbon dioxide and water, right? When all my hair was combusted. That would be an example of of chemical change. All right, so you've got physical change does not alter chemical structure, chemical change does. And those are the two types of change that matter undergoes. All right. Now, when we talk about matter, whoa, let's open a new slide. I want to give us kind of a general scheme by which we can, oh, yes, Susan, totally. Oops. Totally. If you add, butane and Coke, that is a chemical change, right? Or like you drop Mentos into Coke, that is a chemical reaction, totally chemical change. Physical changes tend to be like melting or boiling, right? Cutting, breaking, shaving, those things that don't alter the structure, that just change the size, shape, or phase of a compound. All right. I'd like to talk for a bit about classifying matter. We can break down, so matter's a general category for anything that has mass and takes up space, right? We can take that general category and break it up into smaller, more specific categories. For example, we could split matter up into these two categories. The category of pure substance you can have pure substances, and you can have mixtures. All right, matter can be divided into these two categories. Now, a pure substance, the definition of a pure substance is one thing, right? There's only one thing present. So, for example, distilled water would be pure water, right? Pure substance. Copper wire is made up of copper atoms. That's a pure substance. Mixtures could be are more than one substance. So, like the ocean water, right? The ocean has H2O. It has salt dissolved in it. It has all sorts of animal excretions. It is a mixture of things. It's not just one thing together. My coffee is a mixture of things, right? There's water. There's the brown stuff from the coffee beans. I added a decent amount of creamer. No sugar in this one, but that could be in yours, and that's fine. That would be another example of a mixture. There's more than one thing present in this sample of matter, right? Now, we can further break these down. So pure substance is one thing, a mixture is more than one thing. All right. Now we can take pure substances and mixtures and further break those down into two additional categories. Pure substances can be broken down into what are known as compounds and elements. And mixtures can be broken down into homogeneous and heterogeneous mixtures. All right, so we've got compounds and we have elements, And then we have homogeneous and heterogeneous mixtures. I'm just going to space this out a little better. All right. So first, let's talk about pure substances. Oops. Which can either be compounds or elements. Compounds, in a compound, you have more than one element present. All right, more than one element. In an element, you have just one element. All right, so for example, earlier when I said that a pure substance could be just copper wire, elemental copper, that would be an example of a pure substance that's an element. Now you may be going, how could there be more than one element if it's a pure substance? Well, when I gave the example of water, H2O, that is an example of a pure substance that's a compound, right? Water is made up of two hydrogens and one oxygen together. And in that unit, 2 H's, 1 O, that unit is water. So if you have repeating units of H2O, that's a pure substance of just the compound water, as opposed to an element, there's only one element present. Now, just because you know what's up, Karenessa. Just because there's only one type of atom present in an element, that doesn't mean that there can only be one atom. So, for example, we all need to breathe oxygen, right? Which is an element. Elemental oxygen is, as we know, it's O2. There's two oxygen atoms present in that element. So an element just means that there's one type of atom present, but that doesn't mean there can only be one atom, as you can see with elemental oxygen or elemental nitrogen, for example. So that is the difference between a compound and an element. Now let's look at the difference between homogeneous and heterogeneous mixtures. A great example of a homogeneous mixture is my coffee. All right, my coffee is a mixture, as I said, of water, of the coffee stuff from the coffee beans, and creamer, right? All those things are together, but it doesn't matter whether you're sipping from the top of the mug or the bottom, it's the same all the way through. Homogeneous solutions or homogeneous mixtures have multiple things present, but they're evenly distributed throughout the whole. All right, that is a homogeneous mixture. A heterogeneous mixture would be, for example, if you dumped a bunch of sand into water, what would happen is the sand would fall to the bottom. There'd still be some water down there, but it wouldn't be the same through. You wouldn't have an even distribution of sand and water through the entire thing, because you'd have most of the water up top and then most of the sand down at the bottom. So homogeneous, the same all the way through. Heterogeneous, different depending upon the region of the mixture you're looking at. All right? So this is kind of our introduction to matter, different ways of looking at, analyzing, breaking down this very, very general category into more and more specific categories. There's some homework problems that deal with differentiating types of matter: pure substances, mixtures, heterogeneous, homogeneous, elements, and compounds. You'll see that in the homework set on Canvas. All right, now, oh, there's a fun squiggle. All right, Now, I want to do a little bit of an intro to the periodic table, just so that some of us may already be familiar, others may not. I just want to make sure and go over this so that we're all on the same page. So here's a little intro to the information on the periodic table. All right, so if you look at the periodic table, oh wow. Let me scoot this down. All right. So if you look at the periodic table, okay, there we go. Okay. So the periodic table here, there's an array of elements. It has kind of a funky shape. We'll be talking definitely more about that later. But I want to, for a hot second, kind of zoom in on an element and just kind of unpack the information that you can find buried on the period or included in the periodic table. So if we take a look for a second at everyone's favorite element, silicon, all right, you'll notice that there's a bunch of numbers. Some periodic tables will include the names of the element underneath, and then there's usually another number buried at the bottom. Now, this number up top, right here, this 14, this is called the atomic number. All right, the atomic number, and it tells you the number of protons that element has. All right, the number of protons is the atomic number. All right, right here, this is known as the elemental symbol. All right, and I'm actually going to zero out our periodic table just to make some room. All right, so we have our elemental symbol right here. It's either made up of one letter or two letters. Down here you have the name, and then the number right at the bottom. This is called the atomic mass. Sometimes it's called the atomic weight. Weight and mass are kind of used as interchangeable terms, and if you're a physicist, you'll balk at this because you'll say, like, no, weight and mass are different, and that's correct. But they're related. They're almost the same thing. Weight is equal to mass times the gravitational field constant. So that's why we use them interchangeably. All right, now I want to take a moment and kind of belabor a point about elemental symbols. Now, I said that sometimes elemental symbols are only one letter. Sometimes they're two letters. And the first letter is always a capital. All right. First letter is always a capital. The second letter is lowercase. All right, first letter's capital, second letter's lowercase. And the reason, you may be going, okay, Josh, why are you making a big deal out of this? The reason why I'm belaboring this point is sometimes it can make a big difference. For example, if you look up the element cobalt, all right, cobalt has an elemental symbol of CO. But note, if you don't write the second letter as lowercase, this is not cobalt. This is the molecule carbon monoxide. All right, so you've gone from talking about cobalt, which is a metal, to carbon monoxide, which is a gas that can poison you to death, right? These are two very different things. So you need to make sure that that second letter, this second letter right here, has got to be written small. All right? It's got to be. It makes a very big chemical difference if you don't. Now, I'm not like super aggro about it being lowercase. For example, if you look at the element iridium, iridium has an elemental symbol IR. I don't care if you write it as a tiny uppercase R or as a lowercase r. It doesn't matter to me. It's as long as it's small, I'm fine with it. Okay, but it has to be small. If you write it the same size as the first element, that's gonna cost you points on exams, on homeworks, etc. So just make sure that that when you're writing out elemental symbols, you don't get sloppy with the second letter. Cool? All right. All right, and if you can believe it, that is the end of chapter 1. Let's go ahead and dive on in. We're going to start chapter 2. All right, so chapter 2. Chapter 2 is all about measurements. All right, measurements. So, as we've been talking about, right, chemistry is a physical science, right? We're out in the world, we're making observations, we're writing down things, we're taking measurements, and that's the heart of a physical science, is taking measurements. That is the data we collect, and then we interpret that data, right? Now, we're used to thinking of units in terms of the English system, or most of us are, if you grew up in America. But in the scientific community, there is a uniform system of measurement called the metric system. All right, and that is the system that we will be using in this class. And the English system kind of drives me crazy, especially because the thing that drives me craziest about the English system is I think in terms of the English system. Like, I think in terms of, like, miles per hour is how I think of speed, or distances in miles. And the metric system isn't intuitive to me for lengths. For volumes, it's more intuitive, because that's kind of, what I did in grad school, a lot of measuring volumes and whatnot. But I wish that I had been taught the metric system in school, so it would be more intuitive to me. But anyways, that may never happen. Anyways, let's talk about the metric system. So, the basic unit for length... Oh, hang on 1 second. There we go. The basic unit for length in the metric system is the meter, which 1 meter is about 1.09 yards. All right. The basic unit for mass is the gram, right? Represented with a G, and there are about 454 grams in 1 pound. All right, so the pound is a much larger unit. Technically, pound is weight, gram is mass, but nobody deals with slugs. So, slug, if you're like, why is he talking about slugs? I thought this was chemistry, not biology. Slug is the official English unit for mass. So grams and slugs both measure mass. Pounds technically measure weight. But anyways. When we talk about the unit for volume, the basic unit for measuring volume in the metric system is the liter, which is abbreviated with an L, and, sorry, not a lowercase cursive L. A liter is a uppercase L. 1 liter is roughly equal to 1.06 quarts. So a liter and a quart are about the same. Now, the reason why... Oh! Before we leave off, just one quick side note here about volume. If you are going into the medical field at all, you may be come across a unit called a volume unit called a cc. Right, or if you're watching some like doctor show in the ER, it's like, give them 30 cc's of blood, whatever. 1 cc, this stands for cubic centimeter, or centimeters cubed, is the same thing as 1 milliliter. So that's just something to know. 1 cubic centimeter is 1 milliliter. It's actually a metric unit. All right. Now, one of the reasons why the metric system is preferred over the English system is, in the English system, we have a bunch of different units for the same thing, right? You want to measure a length, you measure it in miles if it's long, or yards if it's medium, or feet or inches if it's small, but they all have different conversion factors. Nothing's uniform. In the metric system, they use prefixes that are all based on powers of 10. So you could have a meter... for measuring medium things, or a centimeter, or a kilometer, and they all scale by factors of 10. It's a very, very logical system. It's very systematic, and so that's why it's preferred for sciences. And you can use all of these prefixes no matter what unit you're using. It could be meters, it could be liters, it could be grams, and you can use all of these base 10 prefixes. All right, they all apply. Now, if you look in the front cover of your book, there's like a billion of these, and you don't need to know them all. And as you already know, I talked last class that everything's open book, internet, other humans, everything, right? So there's technically not a need to memorize anything in this class because you can always look it up. However, I would recommend memorizing these because when you're doing problems and you're in a time crunch, it is worth your time to know what these are off the top of your head so you don't have to look up in a book and waste time finding what these values are. They're worth committing to memory. So I'm not going to force you to memorize anything, but I would recommend memorizing the following list of prefixes. Again, not the gigantic one in the book, but the few that I'm going to give you right here. So name, prefix, and then our unit multiplier. All right, so the first prefix name you probably already heard before, and it's kilo. The prefix is K, and the multiplier is 10 to the third, right? Because kilo means 1,000. Next would be centi, which has a prefix C, and it's 10 to the negative 2, right? It's a hundredth. Next we have milli, which has a prefix of M, and this is 10 to the negative third, thousandth, followed by micro. Now micro, they've already used M for a prefix, so they steal the M from a different alphabet. This is right here, the Greek letter mu. So it's the M sound from the Greek alphabet, and it represents 10 to the negative sixth. The last one that I think is really good to know off the top of your head is nano, right? We've all heard like nanometers, nanoseconds. The iPad Nano, which that's dating myself now, was the first really small iPad. I remember we gave one to my sister for Christmas one year, and it was super awesome. This is 10 to the negative 9. All right, these unit multipliers you will use very frequently in this class, which is why I am recommending that you memorize these. I recommend that. Totally don't have to. It might save you some time. All right. Now, we are going to practice using these unit multipliers extensively, but before we do, we have to talk about, cover a topic by the name of, significant figures. All right, significant figures. If you have any chemistry in your background at all, you will recognize at least these words. significant figures. You'll have seen them before. Nobody has really, it's just one of those things. Now, we're not going to be able to get into, I'm just looking at our time. We have 12 units. So we're going to dive into significant figures tomorrow at the beginning of lecture tomorrow. But before we leave it with the last remaining few minutes, I just want to make a point. I want to issue a caveat emptor. Caveat emptor is, if you're unfamiliar with this phrase, it is Latin. It's a Latin phrase for buyers beware. All right, it's a Latin phrase that means buyers beware. It's a way of saying like, hey, you better watch out, right? Or protect your neck, as the Wu-Tang Clan would say. And anytime anybody is saying something in Latin, it's nothing short of an academic flex. So yes, I'm totally academically flexing for you right now, but the cool thing is, now you can go flex to your friends when you say caveat emptor and they don't know what you're talking about. They'll assume you're smart, probably because you are. All right, now this is buyers beware, caveat emptor about significant figures. All right, and the buyers beware that I would like to issue, the warning I'd like to give you is this. The correct answer must have correct sig figs. And I know we haven't gotten into what those are. We will soon enough. But the right answer will have the correct number of significant figures. And again, we'll get into all of what that means, how to do that, the method for determining how many sig figures are in your number, how many significant figures should be in your answer when you're doing calculations. We'll dive into all of that. But this is something that you're going to have to get good at if you're going to do well in my course. And that is the buyers beware I wanted to say. There was one semester where you know, in a lab class, right, it's 3 hours long, a couple times a week, and you know, you give a little lab lecture or whatever, and then you just sit there while the students do their experiment, and you know, they'll ask you questions at different points, but you basically just get to sit there and eavesdrop on what everybody's saying. And I remember this one day after I had handed an exam back, so these students had all gone over their test, and you know, the normal range of emotions from happy to sad to bleh, in between, right? And there's this one particularly disgruntled student, and I didn't remember what they got, but I usually know if a student did well or not depending upon how they're doing emotionally that day. And I overheard this. There's a particularly disgruntled student talking to their lab partner, and I heard them mumble under their breath that I was a sig fig Nazi. And apparently they weren't happy with the amount of points they had lost over their lack of correct significant figures. And I don't know, I found that a little ironic that he called me a sig fig Nazi because I'm Jewish. So I thought that was I don't know, I found it funny. But all that to say is this. You want to master what comes next, all right? You really, really want to get your significant figures down because this is something that will be a recurring theme on exams, on quizzes, and homework sets. So you want to make sure that you are dotting this I and crossing this T every time you do these problems. All right, let's... okay, let's see, what's our time? All right. We're going to pause lecture here. Now, the last thing that I'm going to say is today is our first lab office hours. All right, today is our first lab office hours. This will be every Tuesday and Thursday. From 3 to 6 p.m. So I'm going to take a break. We're going to stop the stream here, shut it down, but then I'm going to be back in 30 minutes. If you're wondering what I'm going to be doing in the next 30 minutes, there's a baby that needs to get up from a nap, there's a diaper that needs to be changed, and anyways, I'm gonna do some dad stuff, and then I'll be back at 3. And the format that's gonna take is it's open office hours. So I will be here. I'll be hanging out. There's gonna be no kind of pre-programmed content. All right. So with this time, I'm not gonna give like a lab lecture or anything like that. As I said, the lab portion of this class is electronic, and it's kind of driven by you guys, and you kind of get to go at your own pace, except for while meeting the deadlines that have been set. What I recommend is for you to use this lab time to, if you use this office hours, if you do the lab during the office hours, you have the chance to ask me questions. I'm just going to be sitting here chilling. It could be a lot of dead stuff. You could just, like, it might be a video that's 3 hours long with me going like this, like type, because I'm gonna be working on stuff. I'll be answering emails, I'll be doing lecture prep if nobody's asking me questions, but I am here to be available to you. So if you have questions, even if it's not on the lab stuff, if you want to see examples or explanations, totally come hit me up. So and if you log into the live stream and you see me like staring like a dead-eyed zombie at my computer screen tapping away, don't interpret that as me being unavailable. I'm here for you to answer your questions, but I'm also not going to play on my phone. I'm going to be getting work done if you guys don't ask me stuff. So anyways, I hope that was clear. Are there any questions before I go? If not, I will see maybe some of you in lab, maybe all of you, who knows. And then definitely everybody back, same place, same time for lecture tomorrow. So, anyways, okay, I'm gonna go ahead and put a pin in lecture right here. Thanks for stopping by. And again, party's gonna continue in about 30 minutes for office hours, and then tomorrow we will be mopping up chapter 2. Cool? All right, I will catch you guys later.